In this lesson, we are going to discuss word embedding, specifically Word2Vec. Machines can't understand words like humans do, so we need to represent them in numerical terms. One way to do this is representing each word as a vector. This is called word embedding. Here we have assigned a set of random vectors of size 3 to a set of given words. As we have vectors of size 3, we can represent them in a three-dimensional space like this. Can we do better than just assigning random values? Let's say we get the word delicious which we want to represent using our vector notation. Rather than assigning a random value, it is intuitive to place it close to word cake, as these two words may appear in the same sort of context. If we use the same argument, the word pet shouldn't be that close to words like cake or delicious. It should be placed somewhere away from this set of words. We are going to discuss different ways we can do this. One of the simplest ways to represent words as vectors without context are one-hot encoding and binary encoding. If we consider the context as well, more complex methods like Word2Vec, Glove and Fasttext can be used. Here we first explain one-hot encoding and binary encoding, as they are the starting point for other methods which then try to transform them into vectors with context. However, in this lesson we will only discuss the Word2Vec method, and other methods will be discussed in a different lesson. There are so many words in English language. It can be hard to represent all such words in a machine. Sometimes it is even not needed to represent all words, as there are many words which are not used frequently. When we select a finite set of words, depending on our application, that set is known as a corpus of words. If we select n words, to represent them using one-hot encoding, we have to use a vector of size n. As an example, let's say we are going to one-hot encode 6 words. It will look something like this. If n is very large, the encoded vector will be very large as well. If our corpus has 1000 words, this vector will be a vector of size 1000. One option would be to use a binary number to represent each word. If there are n words in the corpus, we only need log n bits. The same sort of words now can be represented using a vector of size 3. Now let's try to understand how Word2Vec works. To find a similarity between words, one of the most common methods is to use the frequency that words appearing together in sentences. Before going into details of Word2Vec, let's understand two methods used to represent information in documents in a numerical manner. Those are bag of words representation and n-gram representation. Word2Vec uses similar wordings to explain slightly different ideas. To make these differences clear, first we explain the bag of words representation and n-gram representation. Let's consider bag of words representation. As an example, assume we have a document. Usually we select a set of words we think would be important as shown in the previous example, which we called as a corpus. Here we have selected 10 words in our corpus. When we put them in the corpus, disregarding the order of those words, we call it a bag of words, as things get shuffled when we put anything into a bag. To vectorize the document, if we want, first we can arrange those words in the alphabetical order. This is optional. In the bag of words representation, we put the count of each word in the document in front of those words in the corpus. Now we can disregard the words and just extract the count as a vector. This gives us a compact representation of the document in vector form. If we have another document, which we call as document 2, we can have another vector representation for that, depending on the occurrences of each word in the corpus. When we have vector representations like this, we can easily measure the similarity between such documents. In the n-gram representation, we are mainly concerned about the co-occurrence of words. That is how frequently words appear together. Let's consider the example document we have here. Sometimes we have to remove unimportant words like prepositions from the document. This is done as a pre-processing step. In this lesson, we are not covering pre-processing. There is a separate lesson on that. In the simplest form, we can consider each word individually. Here we have words in the document one by one, starting from word machine up to algorithms. This form is known as 1 gram. If we group two words together that are close to each other, it is called 2 gram. Here the first two words are machine and learning, so they together form the first element. Then we can have learning and study together, then study and computer, and so forth. We can extend this to any number of words, so it is termed n-gram. When we are grouping words in n-grams, we can group after skipping intermediate words. For instance, in one skip 2 grams, we group machine and study together after skipping the intermediate word learning. Similarly, learning and computer can be grouped together after skipping the intermediate word study. In one skip 3 grams, 3 words are grouped after skipping each consecutive word. For example, we can group machine, study, and algorithms by skipping intermediate words learning and computer. If we skip 2 words, it is called 2 skip 3 grams. In general, we call this k skip n grams if we skip every k intermediate word when selecting n words. With that understanding, let's get back to Word2Vec. In Word2Vec, there are two models to encode words as vectors with some information about context they appear. Those two are continuous bag of words method or CBOW model and the skipgram model. They have similarities with the concept of bag of words and k-skip n grams we learned. But they are not the same. CBOW and skipgram are rather two modeling techniques based off neural networks. In continuous bag of words, first we start off with one-hot encoding of words. Let's take the same 6 words we used in one-hot encoding example. We are going to encode these words using Word2Vec. Word2Vec tries to find the context by looking at frequency of co-occurrence of words in a sentence. Let's consider a sentence. Here we have Lion King tastes zebra, world tastes cake. To find the co-occurrence frequency, Word2Vec first one-hot encode these words and then take the sum. If we take the sum of one-hot encoded words, we can see the resulting vector has the frequency that each word is appearing in the sentence. As taste is appearing twice, the resulting vector has 2 in the corresponding location. In this sense, it is similar to bag of word representation. In Word2Vec method, this result is called continuous bag of words. To encode each word using continuous bag of words model, first we select the target word. Let's assume we are going to encode the word zebra. Other words surrounding this can be regarded as context words. Here we have 3 words before the target word and another 3 after. Depending on how we want to model, we can decide how many words we are going to select as context words. Let's select 2 words before and 2 words after as context words. Let's arrange them as inputs to the CBOW model and output, where the output is a target word and the input is the context words. Now we can start off by one-hot encoding the words. Then the first step is to get the continuous bag of word form by adding them together. To relate this with the target, we can connect this to the target output through a neural network. As we want our encoding to be in a lower dimensional space, the arrangement of neurons should follow a similar form to autoencoders, except the fact that input and output are not the same as in conventional autoencoders. Similarly, in another training sample, we can use the word taste as the target word and its surrounding words as context. This sample can be fed as another training sample into our model. If we continue the process, our model will get trained to produce something like the target word as the output when context words are provided as the input. In an autoencoder, the middle part has a lower dimensionality. If we read the values from this section, it will give a mapping from the higher dimensional one-hot encoded vector space to a more compact vector which is called the feature vector or the word vector. In the original paper, this concept has not been properly explained, but this is the most intuitive explanation we can think of. When the model is well trained, we can input the context words of a given word and extract the values of the autoencoder where the dimensionality is lower. Now let's move to skipgram model in Word2Vec. In the skipgram model, we remove the target word and set that as the input to a model and select the context words as the output. That means we are going to model the context words. When selecting the output words which we are going to model, we skip the target word. Here it is zebra. As we are skipping the target word, this looks something like k-skip n-gram representation we learned. Therefore, in Word2Vec, this model is called the skipgram model. Now, let's arrange our input and outputs as before. First we start with one-hot encoding. Then we can connect the input word with the output context words using a neural network. Here the complexity can be reduced by employing hierarchical softmax optimization. After training the model, the encoded word can be read from the autoencoder. In this lesson, we talked about one-hot encoding, binary representation and Word2Vec embedding of words. We will discuss Glove and Fasttext in a separate lesson. If you think this lesson is helpful, thumbs up and subscribe to our channel for similar videos.